Here we go. Lesson 1-3 is about something called the definite integral, aka distance is a rectangle. I'm going to level with you. You've been letting yourself go. And so today we're going to get you back in shape. Let's imagine that we're going to go for a run, and you're going to move at a rate of 5 meters per second, and you're going to do that for 6 seconds. Question: how far did you run? Answer: well, the distance that we run is equal to the product of two things. The first thing is our velocity as time goes by, and the second is the change in time. So in the case of this problem, we can say 5 meters per second multiplied by 6 seconds is equal to, the seconds cancel and we get 30 meters. Now I challenge you to think about this graphically. Let's sketch a picture. So here's the time, here's the velocity as a function of time, and right now our velocity is constant. So at 1, 2, 3, 4, 5, I'm going to draw a horizontal line that runs for 6 seconds. So here's 0, here's 6 when we stop, and notice that we have a, ta-da, rectangle. And guess what? If we find the area of this rectangle, well, the height is always 5, and the base, which is incidentally equal to how much time goes by, is 6. So 5 times 6 is equal to 30. Translation: when we found 30 meters, we were really finding the area of this rectangle. Now, imagine that we go a step further. It's day 2. We're going to do some running, but this time you run for 6 seconds where your velocity is not constant, it's variable. And suppose that it's given by the equation 2 times the square root of t plus 1. All right. Well, we're still going to use the fact that distance is equal to the velocity over time times the change in time. The only problem is we don't really know what to plug in for velocity. And so what we're going to do is, again, try to think of this thing graphically. Here's time going by, here's the velocity, and I know that at time 0, if I plug 0 in here, we get a velocity of 1. And at time 1, if we plug 1 in here, we get a velocity of 3. And at time 4, I'm picking 4 just because this is a square rooting function. If we plug 4 in here, we get a velocity of 5. And so our graph is going to look something like this. Now, here's time 6. And just like in the last problem, where the area underneath our horizontal line gave the distance, the area under our curve is going to give us the distance because this is velocity multiplied by time. The thing is, since we don't know how to find the area of this, what I'm going to do instead is I'm going to break it up into little sections, so that each section has a width of 1. And then what I'm going to do is I'm going to put a cap on each one of them. Now I'm putting the cap in a specific spot. I'm putting it here because if I put it here, I've missed a little bit of the area. See that? But I've also gained a little bit of area, and I'm going to say that those two are about the same. And let's say that the height at this moment is 2.2. Well, if I continue doing that, I will get a series of 6 different areas, and those areas should be able to approximate the distance.